So in the previous video, we talked through the different formulas for doing the different confidence intervals that we might be interested in doing during logistic regression. Now we want to talk about how to use R to do these calculations for us. So I'll kind of go back and forth between our actual document here as well as R. That way I can label a few different things in our document as we're going through here. So the first thing we're going to do is I'm really just going to be looking at that same model. So I'm just going to store that summary of mod.fit into something. Now we've done summary of mod.fit before, so let me actually just kind of spit that out here first. So we've done that before where we actually get the output. I'm now just going to store that in something because I want to use it later. So now when I run this actual whole line of code, it's not going to spit anything out because it's just storing it for me. And now that I've run that, I'm going to print out the different names, or basically the different things that have been stored inside of sum.mod.fit for me, so I can know what I could ask for. So it spits out all of these different things that are inside of sum.mod.fit. The one here that I'm really most interested in, and the reasoning why I stored it, is because of this cove.unscaled. That's going to be the one I really want here. Because inside of this is going to give me that estimated variance that I need inside of there. So my next line of code is just running that so I can actually see what's inside this cove.unscaled. So what you see here is we have this little kind of 2x2 values being spit out. We do not actually need all of these numbers, but I'll go ahead and sort of talk through what each of these values are. So this first one, this 0.10 value, this is your estimated variance of alpha hat. And I know that because that's the intercept idea. Diagonal from it, and first making sure we feel good with writing here with that scientific notation. So this value here is actually 0.00006,839 value. That is my estimated variance of beta hat. That's actually the one I really want, is that one. Now R was a little weird on how it spit the other two values out because they actually look to be different, but they're actually exactly the same. For some reason they spit this one out in scientific notation, but not this one. But these two elements are actually always going to be the same. Not one that we need to know for really any reason, but for those that would like to know what that value is, that is your estimated covariance between alpha hat and beta hat. But again, really the one I want is this 0.0006839 value. That's that estimated variance of beta hat. So where is that? That is in the second row and the second column of this little thing I just spit out. And so the reason why you're going to see later here this 2, showing up is because it's in that second row and second column. Okay, so now let's go ahead and use this to help us actually calculate our confidence intervals. The first one we're going to do is the one for beta hat, or technically for beta using beta hat. So what I need is my beta hat. And we've used that number a lot before already. I need to get my Z, which will be based upon my confidence level. And then I need this estimated variance of beta hat. And that's what I just found. So that's what I need to construct my interval here for beta. So talking through the code. So first, I'm just going to use a basic 95% confidence interval. So that's why my alpha is going to be 0.05. That beta hat is in the second element of the mod.fit $ coefficients. Again, that's going to be that negative 0.1145 that we've seen before. So let me actually just run that code to kind of remind you what's inside of that. So it has that alpha hat and that beta hat. Again, I want to get that second element, so that's just why I have the 2 part there. And then I'm going to have my z, which is just that Q norm that we've seen many, many times before. But then I want the square root of that estimated variance of beta hat. So I'm going to get that estimated variance of beta hat from that Cove unscaled thing that we were just looking at, but then I'm going to need to take the square root of that as well. So that's all I'm doing next here is I'm taking the square root of this sum.mod fit $cove.unscaled. And again, I want that second row and second column. Same thing for the upper, with the only difference being that plus sign here. And then I'm just spinning it out in a little bit nicer of a data frame here for me. So let's go ahead and run all that code. So here now is my confidence interval for beta. Okay. So that's our confidence interval for beta. Now suppose we want to do one for the odds ratio. And I'm going to go ahead and do one of the harder ones where we actually have that C involved, where C was 10. All right, so again, kind of first, let's go back and just look at the formula that we had for our odds ratio here. So I'm going to want e to the C beta hat. My C is 10. I already know my beta hat. My z was based upon that significance level, or alpha of 0.05. Our C is going to be 10. And we already have this estimated variance of beta hat because it's the same one that we had up here. So now we're just going to program that here in R. So talking through it. So for our lower, it's going to be e to the c, which is 10, times beta hat, which was just in that mod.fit $ coefficient, that second element, minus here first my z, times my c, times that same square root that we had up here as well. Same thing for the upper except for a plus sign. And then I'm just spitting out that information as well. To get my theta hat though, I made sure I did the math here to actually get that estimated odds ratio as well. All right, so first running all of that code. If you recall, here I did actually get a value that is less than 1 because that meant that our odds of success were actually lower when our distance increased by 10 yards, which makes total sense. So that's why actually here I'm going to invert everything. So I don't have to redo any calculation here. I've just got to actually do the inversion. So I'm just going to create my new data frame. My new theta hat, I'm going to call it theta hat.invert, so I realize I've flipped it now. It's going to be 1 over what I had above. But now my new lower will be 1 over the upper I have here, and my upper will be 1 over my lower that we have there, and then just spitting it out. So we now have our new estimated odds ratio once I invert it, but now we're looking at a 10-yard decrease in distance. And we have our new lower and our new upper there. Let's take a moment to actually interpret that interval just to make sure we feel okay. All right, so I would be able to say here that I am 95% confidence that the odds of a successful place kick technically here to an unsuccessful place kick are between 2.672, let's say, and 3.695 times as large when distance is decreased by 10 yards. All right, so a few notes here, and then we'll interpret our interval for the beta that we did as well. So again, I saved that summary.mod.fit that we hadn't saved before, so I could actually get that estimated variance. So to get that estimated variance of beta hat out for me. And that thing is just called, it's called a variance covariance matrix because it gives you all variances and covariances inside one spot. Now that we actually have a confidence interval, what could we conclude about the null hypothesis that beta was equal to 0? Well, if I go back and look at our confidence interval that we got for beta, it's between negative 0.13 and negative 0.098. So I could conclude that beta is actually less than 0 because my entire confidence interval for beta is less than 0. Then that actually begs the question of how would you interpret this confidence interval that we actually just got for beta? What actually makes this interpretation feel a little strange is that it's not really a slope, it's just beta. So how we're going to interpret it's going to feel very weird compared to most other confidence intervals that we've done. So I could say that I am 95% confident that beta, and this is actual beta, right, not beta hat, is between negative 0.1307 and negative 0.0983. Or, I mean, in a sense, well, that there's a negative relationship going on between distance and your probability of making a place kick. But again, it's not a linear relationship, so it feels a little weird to interpret this confidence interval because there's really not a lot of context to give this confidence interval. All right, last we're going to do the confidence interval for pi. Now, if you recall, we've actually done a confidence interval for pi in the previous module, or just the GLM, because we could do it for any of the 3 different link functions that we did. But we're going to do it in a better way, and we'll talk about, again, why the other way that we did it before is maybe not the best way. And so we'll actually go down here to the not as good way as a little refresher. So there was this predict function that we used, and there were 2 different ways that we could predict. We could use the type equals response, which already gave us things in terms of pi, or we could use the link. And we talked about before that this response already gives us the values of pi, so that kind of seems like the way that we'd want to do it. We could get the standard error, and we could construct our confidence interval that way. Well, the reason why that way is actually not as good is this will not force the interval to be between 0 and 1. And so you will actually get slightly different values because of where that normal curve is being expected to have actually been. So we're going to get different standard errors and we can get different intervals. So with the better way, we're actually going to be using the link way of doing it and then actually now then transforming it into what we actually want after we do it that way. So quick understanding here of what we're going to be doing. So when I'm going to be using the link piece and not the response piece, it's going to be doing basically just this piece here for me. It's going to do that alpha hat plus beta hat times x plus or minus the z times that estimated variance that I want. So the values it's going to give me are the fitted values, which is in a sense just that alpha hat plus beta hat times x piece. And then it's going to give me the standard errors of each of those pieces that I need. Or again, trying to translate it back here. The fit is just going to give me the alpha hat plus beta hat times x. I have one for 20 yards and one for 50 yards. And then that standard error, it's a standard error, so it's already done the whole square root of this piece here for me. Okay? So it's done part of it for me, but it's again not quite what I want. So for my lower, I'm going to first do it for my lower in my linear predictor sense. So again, I'm just going to be doing what's in the exponent, and I'm going to raise things to the e at the end, just like what we did when we did a relative risk or an odds ratio confidence interval. We did that one piece first and then took the e to it. We did it on like the natural log scale to begin with. We're going to do the same idea here. So I'm just going to take my alpha hat plus beta hat times x minus my z times that standard error. Same thing with the upper with just the plus sign instead. Now to actually get what I really want, I need to take e to that interval that I just found over 1 plus e to that interval that I just found. So that's what I'm doing in that next line of code here. Is I'm taking from my actual lower is going to be e to that value over 1 plus e to that value, upper e to my upper over 1 plus e to that other upper. Now spitting it out, I actually got everything here so we can kind of just see how it actually worked. So I spit out the distance, that estimated linear predictor, so again just that alpha hat plus beta hat x, that number we have up here. The lower on that linear predictor scale, our estimated probability of success, and then the actual lower and upper on this correct scale instead. And so you will see we actually will get a slightly different looking interval using it on the correct scale, where now we know things are going to be bounded between 0 and 1. Then with the way we did it before was not going to guarantee that things stay between 0 and 1. So just for comparison, so for the 20 yard, when we did things on the link scale first, we get a confidence interval of about 0.9592 to 0.9787. But when I did things on the response scale to begin with, we do get a slightly different looking confidence interval. So the moral right now with the probability of success, this is the better way to do it. The reasoning we want to truly actually do it that way is to make sure that we have things bounded between 0 and 1, since we are trying to find the probability of a successful place kick. Versus when I did it the other way and I've already taken things off of that scale, it's not going to force things to be between 0 and 1. Okay, so some little notes about this. When I want to use that predict, the data to be predicted must be in a data frame with the same variable name as the original data set. What I mean by that, as a little reminder. So this OBS, the ones I'm interested in are 20 and 50. I put that in a data frame, and I made OBS called distance, or DIST, because that's the exact same thing that it was called up here where we fit the model. So that variable name that I actually have in that mod.fit needs to match what we are doing down here as well. That's what that first part means. Again, the second method was what we did before. As long as the probability is actually not too close to 0, 1, the results are not going to be that different. But again, it's always better to do things on that length scale to guarantee that things are between 0 and 1. There are better ways to calculate a confidence interval for a lethal dose than what we talked about previously. So kind of showing you what we talked about previously with that. Is we said we could just do this x hat plus or minus the z times standard error. So there are also better ways to do that. They're a little bit more involved, so we're not going to talk about it for our class, just because, again, it's a little bit more complicated than even the stuff we just looked at, even in terms of pi. Right. Hopefully we feel pretty good about these confidence intervals. I'm using R to do majority of the calculations here for the confidence intervals. Those estimated variances, I would never expect you to get anywhere besides R to get those values. As we kind of move further through the notes, what we're going to be doing is now allowing to have more than one explanatory variable. Because there could be other things out there that predict the probability of making a place kick besides just distance. And I might want to figure out, well, what things should I use? So we're going to do model building as we continue on.